Welcome back to the Deep Dive. Today, we're really digging into something quite ambitious.
We are. It's a framework called Graviton Pressure Theory, or GPT.
Right, GPT. And we're focusing specifically on Sharif Ali Rashada's Part 10, which is all about practical exploration, testable ideas.
Exactly. The goal here isn't just abstract theory. It's about how GPT translates its core ideas, these proposed physical mechanisms, into things we might actually observe or even use. And
the core idea is, well, it's a pretty radical departure from general relativity, isn't it?
It really is. GR describes gravity as curved spacetime, a geometric effect.
Elegant, but maybe descriptive rather than explanatory.
That's the GPT perspective. GPT aims for a unified causal model. It replaces the geometric picture with something physical.
So the big question we're exploring is, what if gravity isn't warp space, but actual physical pressure?
And dynamic pressure at that, generated by what the theory calls self-repulsive gravitons continuously interacting.
So gravity becomes this active field shaped by how these gravitons flow and push.
Precisely. An anisotropic flux, meaning it's not uniform, it's directional, shaped by mass, it's responsive.
Okay, let's start where GR often shines. Light, gravitational lensing, massive objects bending light. GR says light follows a geodesic, the shortest path in curved spacetime. How does GPT challenge that?
Well, GPT fundamentally rethinks how light travels. First, it assumes space isn't empty.
Not a vacuum.
No, it's saturated with gravitons, a field. And light in this view is like a coherence ripple moving through this field.
A coherence ripple. Okay, so if space is this graviton field, this medium, what happens to light ripple when it gets near, say, a star?
Think of the field like an atmosphere, but incredibly dense near mass. The graviton concentration, the pressure, increases dramatically there.
Creating pressure gradients.
Exactly, steep gradients. As the light ripple enters this high pressure zone, it runs into more resistance. GPT calls it coherence impedance.
Impedance, like electrical impedance, resistance to flow.
Sort of, yes. Resistance to the structure of the ripple maintaining its coherence. This physical resistance changes the light's phase, velocity, and its direction.
So the light isn't pulled by gravity.
It's refracted, bent, like light entering water or glass. The graviton field, with its varying pressure, acts just like a lens with a variable refractive index.
Okay, that's a clear physical picture. Refraction, not geodesics. Sounds like optics.
It has optical analogies, definitely, like thermal gradients causing mirages, maybe, layers of air bending light.
Right, but if it's like a lens, does it also slow the light down? GR says the speed of light c is locally constant.
Ah, that's a key point of divergence. GPT predicts that the effective speed of light, let's call it AFESH, actually should decrease slightly in strong fields.
Because of this impedance, this resistance.
Exactly. It's not time dilation causing the apparent slowing. It's physical interaction with the denser medium. That's a testable difference, which we'll definitely get back to.
Okay, so physical pressure bends light. Does it affect other fundamental things? What about redshift? Light losing energy, climbing out of a gravity well?
Yes. GPT reinterprets gravitational redshift too. GR explains it via time dilation. The clock emitting the light runs slower.
And GPT says?
GPT links it back to the coherence ripple idea. As the light ripple moves out of a high-pressure zone into a lower density, lower pressure region,
it encounters less of this coherence reinforcement.
Precisely. The medium supporting the ripple thins out, so to speak. This causes a decrease in energy per unit phase. That energy loss is the redshift. It's a field energy loss effect.
So the redshift and time dilation, are they linked in GPT or separate phenomena?
They're deeply connected. Both stem from the interaction with the graviton field's pressure and density, but the cause shifts from geometry to physical interaction.
Which brings us neatly to time dilation itself. Clocks demonstrably run slower near massive objects. GR has its geometric explanation. What's GPT's mechanism?
GPT calls it temporal drag.
Temporal drag.
Okay. First, GPT defines time differently. Not as a dimension, but as the rate of internal change within any system. Think atomic oscillations, chemical reactions, anything that changes.
Right, the ticking of a system.
And that rate, that ticking, is governed by how much resistance the system encounters from the ambient graviton field.
Okay, an analogy might help here.
Imagine trying to run. Your rate of change. Running through air is easy. Running through waist-deep water, much harder.
The water offers more resistance, slowing you down.
Exactly. The high-density graviton field near mass is like that water. A system immersed in it experiences greater resistance to its internal processes changing. temporal drag.
So the clock physically struggles to tick as fast because of the surrounding field pressure.
That's the idea. It's physically inhibited. This makes the causal link explicit, unlike GR's description of sitting in warped geometry.
That shift from description to causality.
Yeah.
The source material mentions this gives GPT an edge in certain situations.
It suggests so, particularly where gravity fields change rapidly or are very complex. GPT implies you could use detailed gravimetric maps of the actual pressure, to predict localized time dilation perhaps more accurately than GR's smoother geometric approach allows. It offers more granularity.
Okay, from local effects to the grand scale.
Yeah.
Let's talk cosmology, specifically the dark matter puzzle. This is huge.
It is. The galactic rotation curve problem. Stars orbiting way out in galaxies move much faster than the gravity from visible matter should allow, according to Newton and GR.
Which led to the idea of vast amounts of invisible dark matter providing the extra gravity.
Right. The standard model needs about 85% of the universe's matter to be this invisible stuff just to make galaxies hold together and rotate the way they do.
How does GPT explain those flat rotation curves, the velocity plateau, without invoking dark matter?
This ties back to the idea of gravity as an external push rather than just a central pull.
A push from where?
From the ambient external gravitine field pressure acting on the entire galaxy. The visible matter stars, gas, dust, doesn't just exert gravity, it shapes the surrounding graviton field.
How does it shape it?
By interacting with it, displacing it, creating interference patterns. Essentially, the galaxy carves out a kind of dynamic pressure basin within the larger field.
Okay, a pressure basin.
Yes, and the stability and velocity of the outer stars are determined not just by the pull from the center, but by the equilibrium reached within this basin, influenced heavily by the inward pressure from the external field.
So the flat rotation curve isn't anomalous.
GPT argues it's the natural result of this dynamic pressure equilibrium. The velocity plateau just reflects the shape and balance of forces within that basin. No extra unseen matter needed.
That reframes the entire problem. What seemed like missing mass becomes expected behavior of the field itself.
And the source claims this model works well for different types of galaxies, which is important. It also offers a different perspective on things like the bullet cluster, usually seen as strong evidence for dark matter.
Interesting. This idea of a dynamic field also connects to another concept mentioned, the snapback effect. What's that about?
It addresses a potential inconsistency in how GR handles sudden changes in mass distribution, like a supernova core collapse.
GR's geometry updates, but does it happen instantly? What about inertia?
That's the issue. GR doesn't really have an explicit mechanism for field response time or inertia. GPT treating gravity as a physical field, like a fluid. Well, fluids have inertia.
Like ripples in a pond when you drop a stone.
Exactly. If you suddenly change the mass distribution, like that collapsing star GPT predicts the graviton field won't just instantly snap to the new configuration, there will be a dynamic response.
A disturbance.
Yes, a disequilibrium potentially causing the field to overshoot, creating temporary overcompensations, maybe even resonant echoes as it settles back into equilibrium. This is the snapback effect.
So detecting these gravitational aftershocks or echoes
would be incredibly strong evidence for the physical, fluid-like nature of the graviton field, something fundamentally different from static spacetime geometry. A dynamic proof.
Wow. Okay, this brings us to the really exciting part of Part 10, the testable predictions, where GPT explicitly says, here's how I differ from general relativity. Go look for this.
Yes, this is where the theory moves from concept to potential empirical validation. There are four main ones highlighted.
Let's take them one by one first.
Polarization shift. Remember light as a coherence wave. GPT predicts that as this wave travels through steep graviton pressure gradients, its polarization vector shouldn't stay fixed.
Its orientation should change.
It should slightly rotate or shear, because it's interacting with a structured anisotropic medium.
And why is that a killer test against GR?
Because in standard GR, gravity bends the path of light, but it shouldn't inherently twist the light's polarization just by passing through a gravitational field. That's not part of the geometric picture. Finding such a rotation would be direct evidence for the structural interaction GPT proposes.
Okay, prediction 1. Look for twisted light near massive objects. What's number 2?
Non-uniform bending and speed variation. We already touched on the speed variation, but GPT also predicts how light bends might differ subtly.
How so?
Especially near rotating massive objects. The rotation should drag the graviton field, creating more complex anisotropic pressure flows. This should lead to asymmetric lensing patterns, not just bending, but bending unevenly depending on the path relative to the rotation.
GR has frame dragging, the lens thirring effect, but this sounds different, more about the lensing pattern itself.
Yes, it's about a structural asymmetry in the lens caused by the rotating pressure field, going beyond just dragging the path.
Got it. Third prediction. This one involves technology we use constantly.
Right. Satellite time drag. We already know we have to correct satellite clocks like GPS for relativistic effects predicted by GR.
Both special and general relativity, yeah.
But GPT predicts the amount of time dilation, the temporal drag, should be slightly different and more dynamic than GR accounts for.
Specifically when?
Especially in highly elliptical orbits. When a satellite swings in close to Earth at periapsis, it enters a region of higher graviton density, higher pressure. GPT says the resulting temporal drag should be measurably greater at this point than the standard GR calculation predicts.
So we could potentially analyze existing high-precision satellite timing data to look for this extra drag.
That's the implication. Our satellite networks might already hold the data needed to test this prediction, could be hiding in plain sight.
Fascinating. And the fourth prediction, it goes down to the quantum level.
Particle decay rates. GPT suggests the fundamental rate at which unstable particles decay, think muons, kaons, isn't entirely constant, but could be modulated by the local graviton field density.
So if you put these particles in a region of extremely high graviton pressure,
their decay rate might measurably slow down or potentially speed up depending on the field's specifics. This could potentially be tested in labs, maybe using powerful particle beams or near extremely dense materials.
That connects gravity directly to particle physics in a very tangible way.
It really tries to bridge that gap, linking the very large-scale structure of gravity to quantum-level processes.
Okay, let's recap. We've journeyed through GPT's core ideas. Gravity is physical pressure, lensing is refraction, time is resistance or temporal drag, and a potential solution to galactic rotation without dark matter, based on field equilibrium.
And crucially, we've seen how these conceptual shifts lead to concrete, testable predictions, polarization shifts, non-uniform lensing, extra satellite time drag, and variable particle decay rates that could distinguish GPT from general relativity.
It's a compelling picture, moving from abstract geometry to a universe filled with a dynamic, responsive physical field.
Absolutely. The message from this part of the theory seems to be the universe's workings, like light bending or galaxies rotating, aren't just abstract geometric outcomes or mysteries needing exotic additions. They might be the natural, understandable consequences of, as the source puts it, resonance encountering compression, field dynamics.
Which leaves us, and you the listener, with a final thought to chew on. If gravity really is this dynamic pressure-based field, mappable and maybe even predictable in a fine detail, what does that open up?
Beyond astrophysics, could this understanding lead to real-world engineering? If we understand the mechanisms of temporal drag and pressure gradients intimately, could we ever hope to manipulate or maybe shield against or even amplify local gravitational fields? Not just for space travel, but maybe for material science or precision experiments right here on Earth. It's a profound question about control.